Hey folks, my name is Nathan Johnston, and welcome to Lecture 40 of Advanced Linear Algebra. Today we're going to talk about something called the operator norm, which, as its name suggests, is a way of measuring the size of a matrix. Okay, earlier in this course we already saw one way of measuring the size of a matrix. We saw the Frobenius norm, right? But the Frobenius norm, in a sense, it's very, very silly, right? It measures the size of a matrix just in terms of how big are its entries. It doesn't care about where those entries are, so it also doesn't care about how that matrix acts under matrix multiplication. It just thinks of it as an array of numbers without any regard for where those numbers are. Okay, so in other words, it's a norm, but really it's kind of a vector norm. It only cares about the vector space structure of the space of matrices, not the fact that you can multiply them. Okay, the operator norm fixes this problem. Okay, it's a better norm in a sense because it takes into account the fact that, well, when we have matrices, we usually multiply them. Okay, and it takes that multiplication into account. All right, so what is the operator norm? Well, here it is. Suppose that you're working over the real or complex numbers. You've got some matrix. Then the operator norm, we denote it just with these norm bars on either side with no subscript. So if we don't have a subscript, we mean the operator norm. Remember, if we're talking about the Frobenius norm, we would have a little f subscript down there. Okay, so what is the operator norm? Well, there are a couple of different ways that you can define it. One of them is, well, the operator norm, what you do is you take the matrix and you multiply it by a vector and then take the norm of that and then divide by the norm of the original vector. Okay, and then you maximize overall vectors. So in other words, what you're doing here is like this a times v, the norm of a times v here, you think of that at like that's how big is the output from this matrix divided by how big is the input. Okay, so overall this ratio here, it's telling you how much bigger did A make V, right? Like this is the ratio of the size of the output to the size of the input. So like how much did A blow up that vector V? And then you take the maximum over all V's. So in words, what this norm is it's the largest amount by which A can blow up a vector, okay? It's the largest scaling factor that A applies to some vector, okay? Does it make V twice as long? Does it make some vector 3 times as long, or so on? Like, what is that largest scaling factor out of all vectors in your underlying vector space Fn? Okay, so that's what the operator norm is. Another way of looking at it is, well, if you just rescale all of these vectors to have norm 1, then you see that you could also define the operator norm in this way. It's the maximum length of A times V if you restrict the input vector just to be on the unit circle or sphere or hypersphere or whatever. If you restrict it to have length 1, okay? So what is the largest output that you can get if you restrict all of the inputs to have length 1? Okay, that's another equivalent way of defining the operator norm. Okay, it's equal to the original definition as well. Okay, and so yeah, it's just the maximum amount by which the matrix can scale a vector. So if we draw a picture here, okay, sort of based on that second definition, the unit circle definition, okay, if our matrix is 2 by 2, so it's acting on 2-dimensional space, then we think of like the unit circle as the input, and then when we apply a linear transformation or a matrix to it, what happens is that unit circle gets deformed into an ellipse, right? We talked about this, remember back when we talked about the geometric interpretation of the singular value decomposition. So that unit circle just gets deformed into some ellipse that's still centered at the origin. Okay, now the operator norm, it's sort of how far away from the origin is the farthest away point on that ellipse. In other words, what is this length right here? What is the length of the longest axis of that ellipse? Okay, so that length right here, that is that length is the operator norm of the matrix. Okay, but if you think back to our geometric interpretation of the singular value decomposition, we talked about how also that length should also be the largest singular value of the matrix, right? We talked about how the different axes each have lengths equal to the different singular values. So this should be sigma 1, and this should be sigma 2. All right, so this seems to suggest that the operator norm, hey, it's probably the largest singular value of the matrix. Okay, so the singular value decomposition is how we're actually going to compute this operator norm. Okay, but we're going to justify that. Okay, let's go through how do we actually justify that? How do we prove this statement, in a more rigorous way than just drawing a 2-dimensional picture? Okay, how do we prove that? All right, well, we're going to need some helper theorems to get us there. Okay, we're going to need to know some basic properties, some nice things that the operator norm does, and some nice properties that it has before we can prove that, yeah, okay, this operator norm really is the largest singular value. So what are these nice properties that we need to get us there? Okay, the first one, it's called submultiplicativity, okay? And what it is it says if you have any two matrices, Well, if you multiply them together, then the resulting operator norm is never going to be any bigger than the product of the original operator norms, okay? So the operator norm of a product is less than or equal to the product of the operator norms. Okay, so where does this come from? How do we prove this here? Well, what we're going to do is whenever we're proving something about the operator norm, basically we're going to break it down into the stuff that's on the inside of the maximization and its definition. So we're going to look at quantities like this. We're going to look at like what A does to individual vectors. How much does it scale them? Okay, and in particular, what we're going to notice is that the norm of A times V is always less than or equal to the operator norm of A times just the usual Euclidean 2 norm of V. And the reason for this is you can see this just by dividing both sides by the norm of V. Then you're just going to have operator norm of A is bigger than or equal to AV divided by length of V, right? Okay, and certainly that's true because the operator norm of A is the largest quantity that you can get of the form norm of AV divided by norm of V. Okay, so this inequality here, that's true in general, and in fact there's some particular vector v that makes equality hold, right? The one that gets the largest stretch factor out of A, the one that attains equality in the definition of the operator norm. All right, so anyway, that inequality is true in general. And then, so we're going to use that inequality a couple of times, actually. Okay, so what we're going to do is we're going to start trying to reason about the operator norm of A times B. Okay, so to do that, I have to know something about like how much A times B stretches vectors V. So I'm going to look at this quantity. I'm going to look at the length or the norm of AB times V. My first thing that I'm going to do is I'm just going to regroup parentheses. I'm going to use associativity of matrix multiplication to regroup the parentheses over here. And now I'm going to use this inequality over here. If I have a matrix times a vector and then a norm on the outside, well, that's less than or equal to the operator norm of this first matrix times just the vector norm, the length of the vector. Okay, so this inequality just comes from this inequality here. I've just replaced I've replaced V by BV. Okay, now I'm going to do the same thing over here. Here I've got B times the vector. Well, that's going to be less than or equal to operator norm of B times the length of that vector. Okay, and that's good. That's basically what I wanted, actually. Okay, if you take this inequality here, if you take the inequality length of ABV less than or equal to this chunk here and divide both sides by the length of V, then what you get is this inequality down here. The length of ABV divided by length of V is less than or equal to the product of the individual operator norms. All right, and that's so close to what we want because now if you just maximize this inequality over all vectors V, over on the left-hand side here, you're just going to get the operator norm of AB, right? If I slap a maximization over V's on this left-hand side here, then just by definition, I get the operator norm of AB. Okay, and this right-hand side here, I mean, I can't just stick a maximization on the left. If I do that, I've got to stick a maximization on the right as well. But the really nice thing is the right-hand side doesn't depend on V. So if I maximize the right-hand side over all vectors V, I just get the same quantity. I get the operator norm of A times the operator norm of B. Okay, so if I maximize this entire inequality over all B's, well, I just get operator norm of AB is less than or equal to the individual products of their operator norms. Okay, and then I'm done. That's all there is to it. Okay, so yeah, so the operator norm, we say that's submultiplicative. The norm of a product is less than or equal to the product of the original norms. Okay, and we need one other helper theorem to get us what we actually want in this lecture before we can see our computational method for computing the operator norm. Okay, and this other helper theorem that we need says that the operator norm, it's unitarily invariant. Okay, so what we mean by that is if you start off without whatever matrix you care about, and then you just pick any two unitary matrices of your choosing, well, then the operator norm of that original matrix, it equals the operator norm of UAV, right? If you left and right multiply by any unitary matrices of your choosing, well, that doesn't change the operator norm. In a sense, the operator norm is stable under multiplication by unitary matrices. All right, so where's this one come from? How do we prove this? Well, the first step to proving this is to show that the operator norm of any unitary matrix equals 1. No matter what unitary matrix I pick, the operator norm is going to equal 1. Okay, so you can think of this as like this is a helper fact that I need to prove this helper theorem. Okay, so where's this come from? How do we show that every unitary matrix has operator norm 1? Well, again, just think about how much you can scale a vector. How much can a unitary matrix scale a vector? Well, we had a theorem from back earlier in the course when we learned about unitary matrices that said that the norm of UV always equals just the norm of V. That's one of the ways that you could define a unitary matrix. They're exactly the matrices that preserve vector lengths. Okay, so norm of uv equals norm of v no matter what vector v I pick. Okay, well, if I just divide both sides by the length of v, or the norm of v, then I get this. I get norm of uv divided by norm of v always equals 1. Again, no matter what vector v I pick. Okay, so now if I just maximize both sides of this equality, right? If I stick maximization over v on the left and a maximization over v on the right, very similar to what we had up above, then on the left, I'm going to get the operator norm of u. And on the right, I'm going to get just 1, right? This quantity over on the right doesn't depend on v, right? 1 is just 1. All right, so I get, the operator norm of u equals the maximization of that ratio over on the left, which just equals 1 no matter what v I pick. So the maximum is 1 as well. All right, so every unitary matrix has operator norm 1. Now, I'm going to use submultiplicativity, okay? So I've taken care of sort of this helper fact that the operator norm of a unitary is 1. Now what I'm going to do is I'm going to consider this quantity. I'm going to consider the operator norm of UAV. Well, I know by submultiplicativity, right, that theorem that I proved just up earlier on the page, it's less than or equal to the product of the original operator norms. I mean, we proved this for a product of two matrices, but you can very quickly and easily show from that it must hold for a product of an arbitrary number of matrices as well. Okay, so this is less than or equal to the product of the original operator norms. And now I'm just going to say, oh, well, this is a norm of a unitary, that equals 1. This is a norm of a unitary, that equals 1. So those go away, okay? Those two unitary matrix operator norms just go away. I'm just left with the operator norm of A itself, okay? So what I've shown here is that this is less than or equal to this. I've shown that one of these guys is less than or equal to the other one. Okay, so to show equality, now I just have to show the opposite inequality. I have to show that operator norm of A is less than or equal to operator norm of UAV. Okay, and the way to do that is basically exactly the same trick that I just did here, just be a little clever about it. Write A itself in a different way. And what I'm going to do is I'm going to notice that, hey, A, if I multiply it on the left by U star U, it doesn't change it, right? Because U is unitary, so U star U is the identity matrix. And similarly, if I multiply it on the right by VV star, again, it doesn't change because V is unitary, so VV star is the identity matrix. All right, so operator norm of A equals operator norm of this junk, just because those are actually the same matrices on the middle there. But now here's the clever thing. If you group parentheses around these middle three matrices and use submultiplicativity to peel off these two matrices, the U star and V star, then what happens? Well, we can use submultiplicativity again, and I get an operator norm of U star, an operator norm, sorry, this should be V star here on the right, and then operator norm of UAV in the middle, okay? And because this is unitary and this is unitary, they both go away. They both have operator norm 1. I'm just left with operator norm of UAV on the right there, okay? So I get both inequalities, so therefore equality. All right, so that's all there is for that one. Okay, and as a quick side note before we get to the results that we really care about for this lecture, I'm going to note that the same results hold for the Frobenius norm as well. Okay, so the submultiplicativity, it holds even for the Frobenius norm. So the norm, Frobenius norm of AB is always less than or equal to the Frobenius norm of A times the Frobenius norm of B, just like it was for the operator norm. Okay, and also unitary invariance also holds for the Frobenius norm. Okay, if you take the Frobenius norm of UAV, where U and V are unitary matrices, well, that's always just going to be the same as the Frobenius norm of A itself. Okay, so those results are actually quite a bit easier to prove than the results for the operator norm that we just proved. Okay, so these two results for the Frobenius norm, just work with the definition and you can get to them fairly quickly. Okay, but now based on those results, we can show that actually you can express both of these matrix norms in terms of the matrix's singular values. Okay, so suppose that you've got some matrix, it has rank R. Okay, so A has rank R, and its non-zero singular values are sigma 1 up to sigma R. Okay, as usual, with sigma 1 being the biggest one, and so on down the line. Okay, then what the theorem says is, first of all, the operator norm of that matrix, it's just the largest singular value. It's equal to sigma 1. Okay, but also the Frobenius norm can even be expressed in terms of the singular values. And what the Frobenius norm is, well, it's sigma 1 squared plus sigma 2 squared plus sigma 3 squared, all the way down to plus sigma R squared, and then square root at the end of the day. In other words, if you take these singular values and throw them into a vector, okay, so a vector with first entry sigma 1, next entry sigma 2, and so on, then the Frobenius norm of the matrix equals the norm of that vector, right? Like the Euclidean norm of that vector. All right, so where does this come from? Okay, so let's prove this theorem, okay, based on all of those helper theorems that we had up above. All right, so what we're gonna do, first off, you only need to consider diagonal matrices thanks to the magic of the singular value decomposition, okay? For every matrix, you can write in singular value decomposition U sigma V star. Okay, but I mean, both of these norms, we just talked about this. These are unitarily invariant, okay? And U and V star, those are both unitaries. So it tells us right away the operator norm of A equals the operator norm of this matrix sigma in the middle, the diagonal matrix in the middle. And similarly for the Frobenius norm. The Frobenius norm is also unitarily invariant. So the Frobenius norm of A equals the Frobenius norm of that diagonal matrix sigma in the middle. Okay, so we just have to compute the operator and Frobenius norm of that diagonal matrix sigma. All right, so let's start off with the Frobenius norm, just because it's a little bit easier, okay? The Frobenius norm of the matrix sigma, well, let's just write out what sigma is. And here when I've written it out here, I'm assuming that m is less than or equal to n, right? I'm assuming that it has no more rows than it has columns. If it's the other way around, I mean, the computation doesn't change. It's just you'll have a 0 block down at the bottom rather than on the right-hand side. Okay, so if that's my sigma matrix, well, what is the Frobenius norm of that? Well, Frobenius norm is sum of squares of entries square rooted. So hey, it's sigma 1 squared plus sigma 2 squared plus all the way down the line plus sigma r squared, and then a whole bunch of zeros squared. They don't contribute to anything, and then square root at the end of the day. And that's it, okay? That's the entire calculation. That's what we wanted to show, right? I mean, this sum down here, this is this sum up here. We're done. Okay, that's all there is to it. Okay, so basically it just follows immediately from singular value decomposition and unitary invariance of the Frobenius norm. Okay, to do the same thing for the operator norm, we've got to do a little bit more work. It's not too bad, but there's a maximization that we've got to do. Okay, so we want to compute the operator norm of sigma, so let's do that. We want to show that the operator norm of sigma is sigma 1, its first diagonal entry. All right, so what is the operator norm of sigma? Well, it's the maximum stretch that sigma can do, okay? The maximum amount by which the matrix sigma can stretch a vector. Okay, so first, I'm going to show that there is some vector that gets stretched by this matrix sigma by a factor of sigma 1. Okay, and well, you can just eyeball and find a vector that's going to work. It turns out that E1, the first standard basis vector, the vector that has a 1 at the top and zeros everywhere else, if you do that multiplication, matrix sigma times E1, you're just going to get the number sigma 1 times E1, right? It's a diagonal matrix times that vector. You just get the diagonal entries multiplying each entry of E1, okay? So you just get a sigma 1 on the first entry, and then all the other sigmas multiplied by zeros, so they don't do anything. All right, so we just need to compute now the norm of sigma 1 E1, and well, I mean, that's easy to do. It's just sigma 1, okay? It's a vector with sigma 1 at the top and zeros everywhere else. All right, so yeah, the norm or length of this vector is just sigma 1. So I've found some unit vector that gets stretched by a factor of sigma 1. So that tells me that this matrix sigma, has operator norm bigger than or equal to sigma 1. Okay, certainly you can stretch some vector by this factor here. Maybe you can stretch some vector by even more though. Okay, so I've got to rule that out now. I've got to show the other inequality. I've got to show that the operator norm of this matrix sigma is less than or equal to sigma 1 as well. All right, so how do I do that? Well, suppose that you've got just some vector, okay? And then you do this multiplication, okay? If you do sigma times whatever vector that is, and then compute its length. Okay, well, when you do that, what happens is sigma times v, again, this matrix sigma is diagonal, so when you do the multiplication, something very special happens. You just get the diagonal entries multiplying each of the corresponding entries of v, okay? So you get sigma 1 v1 times sigma 2 v2, and so on down the line. Maybe you have some zeros left over at the end. It does not matter, okay? And then after you compute the norm of this guy, again, this is just a vector, so computing its norm is easy. You just take the entries, square them, add them up, and then square root at the end of the day, okay? So this is just the definition of the vector norm, the Euclidean norm, okay? And now here's the clever step, okay? This is really the key step that gets us what we want. Notice that, well, sigma 1 is the largest of all these singular values. So if I replace each sigma j by sigma 1, I certainly get something that's bigger than or equal to this original quantity here. I've just replaced all of these pieces here with something that is bigger than or equal to this piece, right? Sigma 1 is bigger than or equal to sigma j. All right, and that's the clever step, because after you do that, now something really nice happens. There's a sigma 1 in each of these terms in the sum, so I can just pull that out, right? I can pull sigma 1 out of each term in the sum and then pull it out in front of the square root, and I just get a sigma 1 out in front, and then sum of squares of vj's, and then I'll square root it at the end of the day. And this quantity here, that's just the normal length of the vector v. Actually, it's less than or equal to the norm or length of the vector v, because it's only the sum of the squares of the first r entries in that vector, whereas v itself lives in n-dimensional space, right? Okay, so this norm here has a sum up to n, which is going to be, in general, some bigger number. All right, so we get the norm of sigma v is less than or equal to sigma 1 times the norm of v, and then you just do our usual trick here, divide both sides by the length of v, and you'll just find that, hey, norm of sigma v over norm of v is less than or equal to sigma 1. In other words, the operator norm of big sigma, the matrix sigma, is less than or equal to sigma 1. Okay, so that's the other inequality. That shows the other half of the proof, so then we're done, okay? It turns out because we got both inequalities, we actually get operator norm of sigma equals sigma 1, okay? Okay, so that's all there is to it. So let's do a numerical example now. Let's use this technique to actually compute the operator norm of a matrix and also the Frobenius norm of a matrix, even though we already knew how to do that. Okay, so for the sake of efficiency, I'm going to use a matrix whose singular value decomposition we've already computed previously. Okay, so this matrix, we've seen it earlier. This is sort of that 3 by 3 matrix that we saw. It transformed the unit sphere in 3-dimensional space into sort of a squished 2-dimensional ellipse that's just embedded in 3-dimensional space, sort of on an angle. Okay, so we saw a picture of that in a previous lecture, and we showed that singular values are 2 root 6, root 6, and 0. Okay, so let's use those singular values to compute the operator norm and the Frobenius norm of this matrix now. Okay, well, the operator norm is really easy once you have that singular value decomposition. The operator norm just is sigma 1, so you look around, oh, there's sigma 1, so the operator norm, it's 2 root 6. That's all there is to it. You copy and paste. Okay, the Frobenius norm, okay, you have to do a mild calculation here. You just add up the squares of all the singular values and then square root at the end of the day. So sigma 1 squared plus sigma 2 squared plus sigma 3 squared. So copy in my sigmas. There's sigma 1, when I square it becomes 24. There's sigma 2, when I square it becomes 6. And there's sigma 3, when I square it becomes 0. You add them up, you're going to get 30. You square root at the end of the day, you get root 30. Okay, so the Frobenius norm is root 30. And it's maybe a good idea, especially because this is our first time using this theorem to compute the Frobenius norm. Let's compare what we get if we compute the Frobenius norm just via the definition. Remember, the Frobenius norm is just also what you get if you add up the squares of each entry in the matrix and then square root at the end of the day. Okay, so it's going to be 1 squared plus 2 squared plus 3 squared plus minus 1 squared plus 0 squared and so on, and then square root at the end of the day. And if you do that calculation, of course, you're going to find that you get the same thing. You're going to see that you get root 30. Okay, so in practice, I mean, it's easier to compute the Frobenius norm in this way, this bottom method, like just via the definition. That's a quicker method than computing the singular value decomposition. But if you already have a matrix's singular value decomposition at your disposal because of other means, then this other method based on singular values becomes easier. And also, it's really useful for theoretical reasons, okay? It lets us prove inequalities between the Frobenius norm and operator norm, for example. It sort of puts them on a common footing where we can start to compare them to each other, okay? So this formula in terms of singular values for the Frobenius norm, even though it's not necessarily computationally useful, theoretically it's very useful. All right, so that'll do it for the operator norm. I will see you next lecture when we look at one final really neat thing that we can do with a singular value decomposition, which is called low rank approximation of matrices. Okay, so I will see you then.